Hi, welcome back. In this video, we are going to discuss the titration process, difference between endpoint and also equilibrium point, then the pH curve for strong acid, strong base, weak acid, and strong base. Finally, we need to choose the suitable indicator for the titration process. Let's start with tutorial question number 1. Definition for the acid and base indicator. Basically, the indicator are weak organic acid or base, at where they will have a color change in different pH value. B is the endpoint, at where the indicator change color, while for the equilibrium point is the number of mole of acid and base completely reacted. Last, the standard solution is the solution at where we already know their concentration. Now, let's proceed to tutorial question 4 first. In this question, you are asked to sketch a titration curve for the following titration and then suggest the indicator for the following titration and also give the reason. Okay, so we focus on this part first, sketch the titration curve. So when you look at this question, analyte are the species or the substance that we're going to place in the conical flask, while titrant is the substance that we will place in burette. So for the pH curve, the pH will against the volume of substance that added. Since from here we know that KOH is in the burette, so that's why here we will place the substance which are in the burette. So in the conical flask, initially we have the HNO2, which is the acid. So and then this one is a weak acid, so that's why the curve is starting from less than 7 and then going to increasing up to 1 point. They will have a steep part and then continue to increase the pH value because of KOH is keep on adding. So HNO2 is weak acid, KOH is strong base. Therefore, the steep part range in between weak acid and strong base will be 7-11. So basically, we will have the idea that here, the value for here is 7, and then here will be labeled as 11. So the equilibrium point is more than 7. Next one, HCl is the titrant, which in the burette. While the CH3NH2 is the analyte, which will be in the conical flask. So this time for this pH curve, the pH value will getting less and less. HCl is strong acid, while CH3NH2 is the weak base. So the steep part range for strong acid and weak base is 3 to 7. So basically here we know that this one is weak base, so maybe you can like roughly label which is 11, and then the steep part over here is 7, and then over here is 3. Now let's proceed to tutorial question number 3. Figure 1 shows the titration curve between the HBr and also NaOH. As we know, HBr is strong acid, NaOH also is a strong base. So identify the titrant and analyte for the above titration. So based on this question now here, because the pH value is start at 0.3, which is the acid, refer to acid. And we know that if we want to measure the pH value, we will place the pH meter in conical flask. Therefore, the analyte for this titration is HCl, while the titrant will be the NaOH. Next question, determine the concentration of HBr in this titration. So from the pH curve here, we know the pH value. So we're going to use the formula pH equal to negative log concentration H plus, because concentration HBr will equal to concentration H plus due to HBr is a monoprotic acid. So now we have the pH value 0.3 equal to negative log concentration H plus. So when we anti-log negative 3, we will get the concentration for the HBr. Continue with tutorial question 3C. If 0.2 molar NaOH is used to reach the point X, calculate the volume of HBr reacted. So when we look at this point X, and then when going down here is 30 ml. So basically we know that point S actually is referred to pH at equivalent point. So as we understand, the definition of equivalent point is where all the acid and base are react completely. So if we want to know the volume of the HBr, we need to find out the number of mole of NaOH. So how are we going to know the number of mole of NaOH? Given the concentration is 0.2 molar, and then the volume that added is 30 ml, and then we have to convert by 1000, so which will equal to 6 exponent negative 3 mole. Then we need to write the equation HCl and also HBr and NaOH. When they react to each other, they will produce NABr and H2O. Based on the equation, the ratio here in between HBr and NaOH is 1:1. So because this is the equivalent point, so means that number of mole of NaOH will equal to number of mole of HBr, which is 6 exponent negative 3 mole. However, the question need us to calculate the volume of the HBr needed. This is the question mark. In the answer of the question B, the question asks us to look for the concentration of HBr, which is also concentration of H plus and is 0.5 molar. So by using the formula, number of mole is equal to mv over 1000. So if you want to know the volume, means that we are going to use number of mole multiply with 1000 and then divide with the molarity. So when you press the calculator, you will get the answer is 12 ml. So this is the volume for the HBr. Question D, predict the pH at point X, and I need to explain. So when we look at the volume given here, at where the curve also is at the steep part, so we know that it already achieved the equivalent point. So point X is the equivalent point. Due to the HBr and NaOH, both are strong acid and strong base. So when they react with each other, they will going to produce the salt. And then this salt is neutral salt. So that's why the pH will be equal to 7. So basically, this is the explanation why we know that the salt produced, or at this point, the pH is equal to 7. Continue with question E. Predict the pH at half of the equivalent point. So in the previous question, we already know that At equilibrium point, 30 ml of the the 30 ml of the NaOH is used because the titrant is NaOH. So means that if half of the equilibrium point means that only 15 ml of NaOH is dropped into the conical flux. So now in the conical flux, there are NaOH and also HBr. So part of the HBr will react with the NaOH to produce NABr and also form H2O. So we consider that at the initial, there are only 0.2 times 15 ml divided by 1000, which is only 3 exponent negative 3 mole of NaOH. While for the number of mole of HBr will be 0.5 times with 12 ml divided by 1000 equal to 6 exponent negative 3. There is no NABr and also water. So NaOH in this case is the limiting reactant, so it will be completely used up. So we use minus 3 exponent negative 3. For HBr also will use up only 3 exponent negative 3 more due to the ratio is 1 to 1. Then the number of mole of NABr will be increasing 3 exponent negative 3. Finally, after this reaction, there is no more NaOH and the HBr is left 3 exponent negative 3. NABr also have 3 exponent negative 3 more. So now at this condition now, we only have 2 substances in the container which will affect the pH value, which we can see it. One is HBr and then the other one is NABr. So due to NABr is the salt formed from strong acid and strong base, so NABr is the neutral salt. So that means we will calculate the pH value for the HBr that left in the conical flux. So since HBr is the strong acid, so it will dissociate completely. So concentration HBr will be equal to concentration H plus, and it is monoprotic acid. So when we want to find out the concentration, will be the number of mole. In this case is 3 exponent negative 3 mole divided with the volume. So don't forget, in the conical flux, initially there is 12 ml of HBr, which we already calculated in the previous question. And then when at the half of the equivalence point, only 15 ml of NaOH is added. So in other words to say, there are only 27 ml of the solution in the conical flux now. So if we want to do the calculate the concentration, we need to convert the unit ml to liter by multiplying with the 10 to the exponent of negative 3. So press the calculator, you will get the answer. The concentration for H plus is 0.111 molar. Then now you can press the calculator, pH equal to negative log 0.111, then get the pH value. Let's proceed to the last question of question number 3. Determine the point Y. It means that refer to the pH value because the Y is over here. If a completely filled burette is used. So as we know, generally the maximum volume that can measure by burette is 50 ml. Okay, it's used initially for this titration. So we assume that there is 50 ml of all the NaOH are placed or dropped into the conical flux. So now the total volume in the conical flux is 12 ml HBr and 50 ml NaOH, which total is 62 ml. And then we know that 30 ml of the NaOH will cause equivalent point achieved. But then now we add 50 ml, so means that volume excess NaOH is equal to 50 ml minus 30 ml, which is 20 ml. So with here, with the volume of the NaOH, excess NaOH, we can find out the number of mole of excess NaOH, which is using the formula mv over 1000. So m given in the question just now, we already calculate is 0.2, and then left 20 ml, which is 0.20 ml divided by 1000 is equal to 4 exponent negative 3 mole. So the new concentration of NaOH will be equal to concentration of OH negative due to NaOH is monoprotic base. So now if we want to find out the new concentration, again we are going to use the formula number of mole divided by volume in the unit of liter. So 62 times 10 to the power of negative 3 is equal to 0.0645 molar. With the concentration, we are able to determine the pOH value using the formula negative log 0.0645, which will equal to 1.19. We haven't completed the question yet because the question asks us to looking for the pH value. So pH will equal to 14 minus 1.19, which will be equal to 12.81. So the pH value at point Y is 12.81. Now let's proceed to tutorial question number 2. 20 ml of 1.0 molar HCl is transferred to a 250 ml volumetric flask. And then you will add the distilled water is added up to the graduated mark. Then 30 ml of the diluted solution is then titrated with unknown concentrated KOH solution. So means that initially in the volumetric flask, we only have 20 ml 1.0 molar HCl. Then we will add in the water until the mark, which is 250 ml. So this action generally is a dilution process. So if we want to do the dilution process, we have the idea number of mole of the solute before the dilution and after the dilution are the same. So we can use the formula M1V1 equal to M2V2. So before the dilution, the concentration of HCl is 1, volume is 20. Concentration after water is added, we have no idea, but we know the volume of the solution is 250. So the concentration after the water is added will equal to 0.08 molar. Question B. Determine the molarity of the KOH. If we only need 20.5 ml of KOH used to reach the equivalent point, means that we are going to write the equation first. So KOH going to react with HCl, and then we'll produce KCl and H2O. So the ratio here is 1 to 1. So we can use the formula MAVA over MBVB equal to A over B. So concentration acid given in the question is 1 molar. The volume of the acid given here 30 ml is used to do the titration. over the concentration of the KOH, we have no idea. But then they say 20.5 ml is needed. So the ratio is 1 to 1 based on the equation. So now there is only one unknown in the formula. Press the calculator and you will notice that the concentration of the KOH is 0.117 molar. Question 2c. Calculate the pH when the volume of KOH is added is 0 molar. Means that basically we need to calculate the pH at conical flux. So before the KOH is added, in the conical flux, we only have HCl. So don't forget the HCl in the conical flux is the diluted one. So the concentration of the HCl is 0.08 molar, which we obtain from the question 2a. So now, HCl is the strong acid and will dissociate completely to produce H plus and Cl negative. So from here we know that the ratio for HCl and H plus is 1 to 1. So concentration HCl will equal to concentration H plus. In this case, like just now we mentioned, from calculation of answer 2a, we get 0.08 molar. To find the pH value is negative log concentration H plus, which is 0.08. Press the calculator, you will get the pH value is 1.1. So as we already know, the pH meter often read up to 2 decimal place. So it is okay if you put your answer 1.10 as well. Now we proceed to question number 2. When 10 ml of KOH is added into the conical flux. So at this moment now, in the conical flux, have HCl. At the same time, there is also have KOH. Okay, so HCl will going to react with KOH and then produce KCl and water. So again, when this case happens, we are going to use the table ICF, and that must be in the unit of number of mole. So the concentration of acid is 0.08. There are 20 ml. So divide by 1000, it is equal to 2.4 exponent negative 3 mole. So KOH, the concentration in question B is 0.117. And then now only 10 ml is added, divide by 1000. So it's equal to 1.17 exponent negative 3. Initially, there is no KCl. There is no water. So continue here with the changes of the number of mole due to the chemical equation that you write. You will notice that basically the ratio in the equation is 1 to 1. So in this case, the KOH is the limiting reactant. So it will be completely used up in this condition. So we will go into minus 1.17 exponent negative 3. So the KCl will increase 1.17 exponent negative 3, while for the water, we can ignore it. So the concentration, the number of mole of HCl also minus 1.17 exponent negative 3. End up finally, there is no KOH, and then only have 1.17 exponent negative 3 mole of KCl, and also the concentration of KCl is 1.223 exponent negative 3. Then at this moment now, because KCl is formed from strong acid and strong base, again, this is the neutral salt. So they will not affect the pH value. So number of mole of HCl is 1.23 exponent negative 3 mole. But then we need to calculate the concentration of HCl. Due to KOH already added into the conical flask, the concentration of HCl will not be maintained in 0.08. So we're going to use the number of mole that remaining in the conical flask now, divide with the volume. Total volume now, initially there is 30 ml of HCl. Then now we add on another 10 ml of the KOH. So then the concentration of HCl will equal to concentration of H plus, because HCl is a monoprotic acid. Then you can calculate the pH value using the formula negative log concentration H plus. Press the calculator. This is the pH value that you obtain. Okay, now continue with the question C. Calculate the pH when volume of KOH added is 40 ml. So now we know that the new total volume will be equal to 30 ml of the HCl, which is initially in the conical flask, plus another 40 ml of the KOH that we added from burette. So now total volume in the conical flask now is 70 ml. So again, we know that the titration is carried out, so neutralization process is happened. So we're going to write the equation HCl plus with the KOH and then produce KCl and water. So water and KCl can be ignored. So as previously we already calculate, the initial number of mole of HCl is 2.4 exponent negative 3. And then for the KOH, this time the concentration is 0.117, and then the concentration now is 40 ml. So we divide by 1000. The number of mole is 4.68 exponent negative 3. So then it's very obvious, this time after 40 ml of the KOH added, the HCl is the limiting reactant. So all the HCl will be completely used up. While for the KOH, also only 2.4 exponent negative 3 due to the ratio from the equation is 1 to 1. So even though the KCl will also increase 2.4 exponent negative 3, but because we already know that it is the strong form from strong acid and strong base, it is a neutral salt, so it will not affect the pH value. So if you didn't want to write down anything on the KCl and H2O column, is no problem. And then finally, there is no HCl, and then the KOH only left 2.28 exponent negative 3 mole. So then we can convert this to molarity for the KOH, which will equal to 2.28 exponent negative 3 divided by the total volume 70 ml. So press the calculator, you will get it is 0.0326 molar. Concentration of KOH will equal to concentration OH negative due to the KOH is monoprotic acid. Okay, then with the concentration OH negative, we are able to determine the POH value. Press the calculator, the POH value is 1.49. But again, the question is asked us to determine the pH value. So we're going to use 14 minus the POH value, and then end up the pH value is 12.51. Question 2D. State the observation at the end point. If phenolphthalein is used as the indicator. So as we know, in the burette is in the conical flask is the HCl, and then in the burette are the KOH. So phenolphthalein will show colorless when it is in the acidic medium, while the color will become to the pale pink when it is in the basic medium. So the observation here, we will write it down. The changes will be from colorless to pale pink. Last part of the question number 2, draw the titration curve. So basically, we have to plot a graph pH against volume of the solution aided. So what is in the burette? KOH. So the pH against the volume of KOH aided. Indicate all the points from the above calculation. So from the above calculation, we have C1, C2, and C3. So let's check out the equation. Initially is 1.1 when there is no KOH aided. Okay, so when 10 ml of the KOH aided, the pH value is 1.51. At the equivalent point, which is 20.5 ml, the pH value will be the 7 because HCl and KOH are strong acid and strong base. So the salt produced at the equivalent point is neutral salt. The pH value is 7. When you add on all the KOH, over here supposedly labeled as KOH. All the KOH is added up to 40 ml. The pH value already increased to 12.5. Okay, we go back to question number 4, and where we already discussed in question number 1 is in the beginning of this video, we discussed about how to sketch the titration curve. So now you are asked to suggest a suitable indicator. So before we can suggest the suitable indicator, we have to identify first what is the type of the titration in between HNO2 and KOH. So HNO2 is weak acid, KOH is strong base. So the steep part pH range will be at 7 to 11. However, for the HCl, which is the strong acid, and CH3 and H2 is the weak base, so for this one, the steep part range will be at 3 to 7. Okay, after we can identify the steep part pH range, then we can refer to the next table to determine the suitable indicator. Yes, based on this list, basically, we're going to know strong acid and weak base. The steep part pH range is 3 to 7. So this is the pH range for color change of the indicator. So 3 to 7. The color change pH range is is in between 3 to 7, then it will be accepted as the indicator. So except from methyl orange, bromo phenol blue also accepted. Methyl red also can be used to determine the equivalent point or the end point for strong acid and weak base. However, this is the indicator that you can choose for question 4B. So however, for the strong base and weak acid, the range is, the steep part pH range is at 7 to 11. So in this case, 7 to 11, 7 to 11, 7 to 11. So these two, chrysolite and also phenolphthalein, will be suitable as the answer in 4A. So explain your answer. So basically, you can refer this statement. The indicator will work best when the color change is over a pH range that fall within the steep part. So now all this we are choosing is within the steep part. So This is how we determine the suitable indicator for certain type of titration. Okay, these are the final answer for tutorial question 2, question 3, and question 4. So we already end the part of 7.2 titration. In next video, we are going to complete 7.3 KSP topic. So see you in the next video.